Welcome to your second physics video. The topic of this video is going to be a more in-depth look at velocity, right? Some goals for this video. Hopefully by the end of it you will have a bit more of a conceptual understanding of velocity. What do we mean when we say velocity? How is it different from speed? We're also going to take a peek at velocity versus time graphs, how they relate to position versus time graphs, which we spent a lot of time talking about in class today. And finally, we're going to talk a little bit about calculating velocity, right? What does that look like? Depending on where you are in your classwork, some of this might be review. Hopefully, you will still gain something from this video. All right. So without further ado, let's recap briefly. What is velocity? How is it important for our study of how things move, right? Velocity is first and foremost a vector, right? Remember we talked about vectors versus scalars in our previous video. Remember, vectors have both magnitude, right? That is size. I can't spell today. Magnitude and direction. Okay, lots of great questions in class today about the relationship between speed and velocity. To a certain extent, velocity is speed, but with a direction denoted. We're just giving you that extra bit of information so that you can know, okay, which way is this object going? Which way is it? Where is it going to land? Right, and what position will it end in? We're still just talking about position in one dimension, right? We're going to be looking at, for the most part in this video, a number line, right? So straight line with origin somewhere in the center, a positive side, and a negative side, okay? So we're looking here again at motion in one dimension, right? As I said in the last video, one dimension just means that we're on one plane. We're not looking at motion side to side and up and down. We're just looking at motion side to side or up and down. We will get to the point where we start looking at motion in two dimensions, but that's not for a while. So when we're talking about velocity, it's important that we know what our directions are. And to a certain extent, these are arbitrary, right? You denote which side is the positive side and which side is the negative side, right? We have arbitrarily decided what direction is north, south, east, west, right? But you have to tell your reader or me, if I'm looking at problems that you're solving, what direction you consider to be where, right? I could have just as easily here on this number line decided that I wanted to make this side the negative side and this side the positive side, right? It's really up to me. But I have to make that clear so that everyone knows that I know what's going on. All right? So, backing up a sec, right, we talked a little bit about speed a few classes ago. We came to the conclusion, right, that speed can be calculated by dividing the distance traveled right? The distance traveled divided by the time that it took to travel that distance. As you're thinking about this, right, this concept of speed, one question that comes up is, can you have a negative speed, right? Can speed be negative? Well, that's interesting. Can speed be negative? We're just going to give up on writing that part. Right? Can speed be negative? The answer is no, right? You can't possibly move slower than not moving, right? If you cover zero distance, you have a speed of 0. You can't possibly cover negative distance, right? You're always, if you're moving, you're going to move a positive distance, right? So speed is always positive, right? You can think of speed sometimes having, a absolute value bar around it, right? Speed is always positive. Velocity, on the other hand, right? Velocity can be negative, right? So speed, right, can't be negative, right? Velocity can, okay? Velocity can be negative. Okay? And part of this is the negative and positive signs associated with velocity mean slightly different things than we think about them traditionally meaning on a number line. Okay? In the case of velocity, right, just to recap, we defined velocity last video, right? Velocity is the distance traveled, right, per time in a given direction, right? So this first part here looks kind of familiar, right? Traveled, well, I missed a word in there. I could have sworn I wrote distance. This is the distance traveled per time in a given direction. Okay. This first part here looks familiar, right? The distance traveled per time, right? Distance traveled per time. That looks pretty similar to speed, right? Pretty similar to speed. The part here that's new and exciting is going to be the direction piece, right? And direction is often denoted, wait for it, by negative or positive signs, right? So that's where we get our plus or minus, right? Denotes direction. Okay, so what that means, right, is say you've got a line, right? Bringing it back to our good old number line, right? Here's my origin. I'm going to say that this side is the positive side and this side is the negative side, right, in terms of my positions. Again, I could have just as easily decided that this side should be the positive side and that this side should be the negative side. It's up to you, right? But say that I have an object here that starts on the origin, and I'm told that this object has a velocity of 2 meters per second, okay? We're going to assume, right, if there's no negative sign, this is a positive 2, right? Positive 2 meters per second equals, right, the average velocity, right, v bar, okay? This tells me that every second this object moves 2 meters in the positive direction, right? That's what this positive sign is telling me, right? So this particle is going to move that direction, okay? Get this a little more page, right? Same thing, number line, right? We again have a particle starting at the origin, right? I'm going to call this side the positive side again just to keep it consistent. This side will be our negative side, again for consistency's sake. And here's our particle. We're told that this particle is moving negative 2 meters per second, okay? That is its average velocity, right? This particle, just like the one before, is still covering 2 meters every second, except it's going in the negative direction. So it's going to be going the opposite way, right? Technically speaking, right, this scenario has a larger velocity, right? It has a velocity of +2. Positive numbers are bigger than negative numbers, right? However, both of these objects are moving at the same speed, right? They're both covering 2 meters every second, just in opposite directions. So that's the main difference between velocity and speed, right? Is that in velocity, these positive and negative signs denote what direction the object will be moving. So how do we think about this mathematically, right? The equation for calculating average velocity, right, v bar is displacement, right, which we saw in the last video as change in position, delta x, over, right, the change in time, right? How long did it take for that change in position to happen, right? Remember, this change in position is not the same as distance, right? Delta x is not distance, right? The example of this, right, that I gave in class, and I'll show it again just to make it clear, right, is if I start in one position, right, and I travel to another, right, say this is position A here, and this is position B, right, and then I turn around and I walk back to position A, right, we'll call this A, and this B. Let's say they're 1 meter apart, right? The distance I walked, right, is 1 meter there, 1 meter back, right? So my distance is 2 meters, right? Right. My displacement, my change in position, my delta x, right, is 0. You're like, whoa, wait, Miss Mac, that makes no sense, right? Displacement refers to the change in position, right? Through this exercise, I didn't actually change positions. My starting position and my ending position are both point A, right? I move no meters from the start to the end, right? So when you're calculating displacement, right? That's a horrible x. Calculating delta x, right? You're gonna do delta x equals the position that you ended in, x final, right, minus the position that you started in, right? And I did a few examples of this in class, right? So if you start at, say you start on our number line, you start at positive 3. There's positive 3. We'll throw the origin in there just for kicks. Don't want graph paper yet. And you end at negative 3, right? This is 0. This is your x initial. And this is your x final. Your displacement, right, is going to be delta x equals the final, negative 3 is your position, minus positive 3. Right? So your change in position, let's call these, we'll say these are meters, right? So your change in position is negative 6 meters, okay? Pretty straightforward, right? Now, right, if we wanted to calculate the velocity, right, for this change in position, we would need to know the change in time. So let's say that moving from our x initial to our x final took us 2 seconds, right? We were walking for 2 seconds. We need to know our change in time. Change in time is pretty simple. It's still, right, the final time minus the initial time. The initial time in this case is 0 seconds. We didn't start the clock at 1 second. We started it at 0, right, and it counted to 2. There will be cases where perhaps your time initial is not 0, but that's more when you're looking at graphical representations, right? So our delta t is 2, right? Plug those into our equation. Average velocity equals delta x over delta t. That means negative 6 meters over 2 seconds, right? And that equals negative 3 meters per second. Okay, so those are sort of how our calculations are going to go. We're going to do more of those. Actually, you'll probably be sick of them by the end of the week. Okay. Final thing for this video, velocity graphs. Finally, I get to paste my graph paper on here and have it actually stay. When we're talking about velocity, for this first unit, right, remember we're in the constant velocity model, right? So we're not going to deal with anything that has a changing velocity. Whoa, that's no good, right? We're always going to have a constant velocity, at least for this first unit, all right? So that simplifies our graphing, right? If we're going to check out a position versus time graph, right? Let's go. Right, so we have x and t, right? Position versus time, right? We have an object that starts at the origin. Each of these squares I'm going to call is 1 second, right? Similarly, each square on this side I will call 1 meter. Okay, so that's 1, 2, you get the picture, right? So if we start at the origin, try to do a straight line here. Whoa. Right, it's not very straight, but you get the picture, right? I'm trying to hit here just a 1-to-1. These are our points, okay? If this is our position versus time graph, right, I'm going to show you real quick. Our slope of this line, right, slope, as you might remember from an algebra class, slope equals the change in y, right, in the vertical axis, right, or the rise over the change in x, right, or the run, right? So when you're first starting out, right, you might calculate slope by, tracing between 2 points on a line, right? So if we do that here, right, maybe we go between these 2 points, right? That looks like maybe we are moving from 1 meter, 2, 3, 4. So we've got 1 point down here. Our first point is 1, 1, right? And our second point that we're working with is 4, 4, right? 4, 4. Right? So we're going to go ahead and subtract our second point, right? The one with the higher seconds, right? The 4 seconds from our first point to get our slope. So if we do that over here, right, we're going to get 4 minus 1 over 4 minus 1, right? That is going to equal 3 over 3, which is equal to 1, right? But we have to remember, right, that these axes have units, right? This axis here is position, right? So it's going to have the units of meters, right? And our axis down here is time, so it's going to have seconds, right? So we've just actually calculated the velocity, right? This position versus time graph has a velocity of 1 meter per second, right? Anytime you have a position versus time graph, the slope of the line within that position versus time graph is going to be the velocity, okay? Pretty cool stuff, pretty interesting. Now, right, if we were to turn this graph into a velocity versus time graph, we'll just do that right below it, right here. All right. So this will be time here, right? And instead of position, I'm going to put velocity over here, right? So now our units are going to be meters per second on this vertical axis, right? And we're still going to have seconds on our horizontal axis, okay? Right? As you look at this position versus time graph, right? Now we're looking up here, right? The slope of the line, I know that my drawing is poor, but imagine that the slope of the line stays exactly the same, right? It's always 1 meter per second, right? So this velocity graph is actually going to be pretty boring, right? It's just going to be a straight line across at 1 meter per second, right? Because we have no changing velocity. Imagine that I can draw a straight line, right? And for this unit, right, the constant velocity model that's what most of our velocity graphs are going to look like, right? We don't have a changing velocity. There shouldn't be any slope, right, to our velocity. When we get into acceleration, the velocity will change, but that's a story for another unit, okay? So I want to get into here, just do one more example of transitioning a position versus time graph into a velocity versus time graph, and then I'll let you guys get to it, okay? Right, so say we have we've got a position versus time graph. And this will be our velocity versus time graph. Okay. Our right, so let's go ahead and label these axes. Right, that's position. We've got time over here, right? Give us some units so we know what we're looking at. These are going to be seconds. We're going to call these some meters, right? And assume again that every square is 1 meter per second, right? Our goal of this is to transfer this position graph onto this velocity graph, right? Make a same represent the same motion but with different units on our graph. All right, so in order to do that, we first have to solve for the velocity, right, at these certain points, right? So it seems that we have two different velocities represented here in this graph, right? It's not nice and pretty like the one before was, where it was just one line, one slope, right? So we're going to have to do a little more legwork, hopefully not too much legwork, right? But we've got from 0 seconds, right, from the origin right here to 2 seconds is one slope that we'll need to solve for, right? And then we have another slope, right, from 2 seconds on to 5 seconds, right? So within that, right, the slope is constant. It's not a curved line. It's linear, right? But we have two separate constant velocities, right, that we need to solve for. This is convenient, right, because my rise over run looks like it's going to fall exactly on the graph, so I don't need to do too much crazy math. It looks here like, right, we've got one point we could use to solve for our velocity would be the origin, right? It definitely starts there, right? It appears to go through 1, 2, as well as 2, 4, right? This first line, right? And if we count squares, we're going to rise 2, right? And we're going to run 1 square, right? So rise over run, our slope for this first section here is going to rise 2 meters, right? Run 1 second. Okay, so that means that our velocity from time equals 0 to time equals 2 is 2 meters per second. Okay, in that yellow highlighted bit right there. Right? This bit is what I'm talking about. Okay? Right in here. Okay? So now we need to transfer that information onto our velocity versus time graph. Okay? We know that from t equals 0 to t equals 2, the velocity is 2 meters per second, and it's constant there. So we can count up on our velocity axis, positive 1, positive 2. Draw a nice straight line over for 2 seconds, okay? Now we got to look at our second part of the graph, right, where the velocity looks like it maybe changes a little bit, right? You see that in here, this one, okay? Again, right, we can kind of identify points here where the line intersects and talk about our rise over run, right? Find our slope. So it looks to me like we're going to have, again, that 2, 4 point. We can use that as a starting place. 2, 4. And then it also looks like it intersects here, right, at 3, 2, right? And continues straight on from there. So we can use those points to calculate our slope if we wanted, right? We could write out m equals, y2 minus y1 over x2 minus x1, right? Which in this case would be 2 minus 4 over 3 minus 2, which gives us negative 2 meters per second. Okay. Easier way to do this, right, since it looks like these are nice intersects, you can again count the difference in rise over run to get from one point to another, right? So we go down negative 2, right? So we're going to have negative 2 meters, and we go over 1 second to get there, right? So we're going to have, again, gets the same answer. Love when that happens. Negative 2 meters per second, okay, for the purple part of our line. Then we just got to add that in, right? So we've said from 3 seconds to 5 seconds, it's continuing at that velocity. So move on over to our velocity versus time graph, right? Go over to 2 seconds. At 2 seconds, we have a switch in velocity. So it goes down to negative 2, and it's there for 3 seconds, right? If you want to connect these lines, that's fine, or you can leave them as is, but this is what your velocity versus time graph should look like for this. Interesting side note that we'll talk more about in class the next time we meet. Velocity versus time graphs can be really useful because the area between the line of the graph and the x-axis, right, for this section here, it's the one highlighted in red. For when our velocity goes negative, it's the one highlighted in yellow, right? The area of these squares, right, equals, let's see, we'll go area square equals distance traveled, right? Not displacement, but the distance traveled for that object, right? So in this case, right, our starting position is the origin, 0, 0, right? Our starting position would be, our I initial would be 0, and our I final, right, at the end of our graph is right over here. So trace that over is negative 2. Right? That means that our displacement, right, delta x, which is x final minus x initial, right? So that's negative 2 minus 0. That's negative 2 meters is our displacement, right? But our distance traveled is going to be much larger, right? And that's shown by the area in these squares. right? In this case, this is a 2 by 2 square, right? 2 seconds, 2 meters. And this is a 3 by 2 square, right? So that, ooh, didn't mean to write 6. Gave away the answer, right? 3 by 2, right? So if you know your basic geometry, right, the area of a square is just going to be 2 sides multiplied, right? So 2 times 2 is 4, right? And the area of the rectangle is the same thing, right? So 3 times 2 is 6, right? Add those together, right, and you get 10. You get 10, right? And if you think about it, right, one of these numbers that you're multiplying, right, for the first example, we're multiplying 2 times 2, right? But one side has the units of meters per second, right? And the other side has the unit of seconds, right? So if we multiply meters per second times seconds, we end up with the unit of meters, right? These two are going to cancel out. We end up with meters, right? So this is really 6 meters. And I don't know if I can fit this in here. 4 meters, okay? Add them together and you get that this object over the course of this travel, although it's only had a displacement of -2 meters, has traveled positive 10 meters, okay? And with that, you can, of course, solve for this average speed, right, which is going to be different than our average velocity, okay? More on that later. If you still have questions, I'd encourage you to check out Chapter 2 in your textbook. Also, if you haven't finished Practice 2 that I handed out in class, feel free to keep peeking at that. We'll start off next class working on solving those problems.